Today in this lesson we're going to talk about something called a change of state. We have talked earlier about states of matter. We talked about the solid state of matter, the liquid state of matter, and the gaseous state of matter. And we talked about properties of each of those, if you recall. One of the items of discussion was the distance between particles and, of course, how they were arranged related to each other. If we can envision a gas in a jar and a liquid in a jar, and we pretended the molecules were actually large enough to see, which they aren't, we would see that gas particles are huge distances away from one another, as we noted earlier, and liquid particles are really close to each other, in many cases touching each other. For that reason, as you recall, liquids we say are essentially non-compressible, they're incompressible. Well, the discussion today is going to focus around the change of state from the liquid phase to the gaseous phase. This is called evaporation. So how does a liquid phase transform itself into a gaseous phase? How do these particles essentially get farther away from each other? That's our topic of discussion today. Now, to start, in a given sample of a liquid at a given temperature, the average kinetic energy of all molecules is constant. However, in actual fact, the actual kinetic energies of individual particles vary greatly. Now that might sound like a contradiction. Let's read that again. Because when you first read it, you say, Hammer, you just contradicted yourself. You said, in a given sample of a liquid, the average kinetic energy of all molecules is constant, but in actual fact, the actual kinetic energy varies greatly. Which one is it, Hammer? It's one way or the other. Either they're constant or their kinetic energies vary greatly. Well, it turns out in reality, it's both. Let me give you a metaphor to help explain this. Let's say that a class took a quiz, and the score on the quiz averaged to be, 20 out of 25. That was the average score. So let's write average score. Does that mean everybody in the class received a 20 out of 25? No, of course not. Couldn't some have received a score of 25? Couldn't some have received a score of a 2, or maybe a 3, or maybe a 15? Can't the individual scores vary greatly? Yet the average score for a quiz remains constant through classes that are taking that quiz. I hope that helps you understand it a bit better. See, when it comes to the molecular perspective, if I were to look at a liquid particle, so let's just look at, we'll draw a picture of a liquid here. Does that look unorganized enough to be liquid particles? Let's look at that particle. That particle might have more kinetic energy than this particle. However, if we take the average of the kinetic energies of all of these particles at a given temperature, it's constant. So regardless of the temperature, their average kinetic energies are constant. However, within that sample, some will have a high kinetic energy and some will have a low kinetic energy. They don't all have the same kinetic energies, much like your quiz scores. Some could have low quiz scores. Some could really have high quiz scores. However, the average quiz score between classes for that particular quiz generally remains constant. The same thing is true for a sample of a liquid. The particles themselves, their individual kinetic energies might vary greatly. However, the average remains constant. Now remember, we want to talk about evaporation today. In order for a liquid to turn into a gas and evaporate and be in the vapor or gaseous state, the molecule must meet two conditions. Number one, in order for a molecule to evaporate, it must have adequate kinetic energy to escape the attractive forces of its neighbor. And we could say neighboring molecules. So it's got to have enough energy to be able to remove itself from the molecules that are around it. The second, and one that I think is probably more important, is it must be on the surface of the liquid. A molecule cannot evaporate if it's buried between several layers of other molecules. It has to be on the surface. And then, in addition to being on the surface, it must have adequate kinetic energy. Now remember, not all molecules have the same kinetic energies at a given temperature. Some have a high kinetic energy, some have a low. Let's take a look at this graph. So let's look at the blue line first. So T1 is a colder temperature. So you can see T2 temperature is greater than T1. So this is a colder temperature than T2. And so on the blue line, we have molecules with a certain average kinetic energy. Some of those have a high kinetic energy. In fact, some of them have enough kinetic energy that they, if they were on the surface, they could actually leave and become a vapor. So this would be the minimal kinetic energy needed to evaporate. So you can see at a cold temperature, not very many have the needed kinetic energy. Most of them are way over here with a lower kinetic energy. Take a look at T2. This is the warmer temperature. So that would be the red line. If you take a look at this red line, the area that's past the minimal kinetic energy that's needed to evaporate is greater. So at a higher temperature, obviously, more particles have the kinetic energy that's required to evaporate. Now, only a certain number of molecules have enough energy to escape the attractive forces of their neighbor and to evaporate. Those, of course, that are on the far right of the graph. Yet, if I have a drop of water left undisturbed on my tabletop, all of those molecules will completely evaporate if left undisturbed. How do these other molecules acquire the needed energy to evaporate? In other words, where does this energy come from? So if you can imagine my tabletop, and if I have a drop of water on that tabletop, let's say some of these molecules on the surface have enough energy to evaporate. So that one will leave, and another one will leave. Some others don't have the required kinetic energy to leave, so even though they're on the surface, they don't evaporate, they just sit there. Yet, if I leave this drop undisturbed over time, won't that drop get smaller and smaller and smaller until that drop is completely gone? So how do the molecules, A, end up on the surface, and B, get the required energy to be able to escape the attractive forces of their neighbor? Well, the energy comes from the surroundings. Energy from the surroundings is added to this liquid, and as the molecules evaporate, there are other molecules that gain energy from the surroundings that now have enough energy to leave the surface if they're on the surface of the liquid. Because remember, the kinetic energy will always remain constant. So when some with high kinetic energy leave, how is that kinetic energy, the average, going to remain constant? Well, others inside this liquid have to gain some energy to keep that energy constant, and that is gained from the surroundings. I think maybe the best way to explain this is with an example that you've all experienced. Imagine, if you will, It's a hot summer day. It's 90 degrees, and you are hot, and you are fortunate to be living near a swimming pool. So here you are. You're 90 degrees. It's 90 degrees outside. You are hot. You've been running around. You've been exercising, maybe even working in the fields. I don't know what you've been doing, but you are hot. And so you have a swimming pool nearby. And so you say, okay, in order to cool myself off, I'm going to jump in that swimming pool. Now remember, it's still 90 degrees outside. You swim around the pool, enjoy your time there cooling off, and then you get out of the pool. Now think about it. It's still 90 degrees outside. Here you are now standing on the edge of the pool. And what do you start doing? Remember, it's still 90 degrees outside, but you start to shiver. I mean, I've seen little kids with 0% body fat, with their arms held across their chests, and they're shaking, and their lips are blue, and there's goosebumps all over their bodies. But it's still 90 degrees outside. What is happening? Why are those kids shivering when just a few minutes ago, before they jumped in the pool, they were sweating? They were so hot they could hardly wait to get in the pool. What is the difference? Well, this person here that just got out of the pool is now covered in water. What's happening to that water? That's right, it's evaporating. The molecules on the surface of the liquid are leaving, and they're turning into the vapor state. And the kinetic energy of this droplet, kiddo, still has to stay constant. So if the high energy molecules are leaving, doesn't that leave lower energy molecules left behind? Where do those lower energy molecules get enough energy to evaporate and turn into the vapor state? Because eventually this kid over here is going to dry off. Where do they get the energy? Well, they get the energy from the surroundings. And in this case, the surroundings is the body of this kid. The energy from that body is leaving the body, and it's providing energy for those droplets of water to evaporate. So imagine, if you will, energy leaving your body. What's it going to feel like to you? Yeah, you're going to get cold, and you're going to start to shiver. Now, eventually, you're going to stop shivering. When do you stop shivering? That's right, when all of the water on your body has either been toweled off or has evaporated. And then you're this kid again. You're really hot, so what do? Well, you jump in the pool again, and the process begins all over again. So, to wrap this up, in order for a molecule of water, or any liquid for that matter, to evaporate, it must be on the surface of the liquid, and it must have enough kinetic energy to leave the surface. The energy provided for the other molecules to evaporate will come from the surroundings. So we say that the process of evaporation is an endothermic process. That means it requires energy. All right, that's good enough for now. We'll talk to you soon.